different context.
Okay, thank you very much. First of all, I would like to thank the Institute and the organizers for the opportunity to give this seminar. I'm going to talk about the topic which is, I can say, rapidly growing. I will focus on particular aspect, mainly on something which we call the genuine dynamics of quantum systems in particular theory. And for obvious reason, the details I'm going to present will be mainly focused on this part of the field in which to which I contributed. So let me maybe start by very boring motivation why we even consider quantum gravity. We know that currently in theoretical physics we have two main theories, two pillars of modern theoretical physics, which is general relativity, of which main property is that in general, roughly speaking, matter, content and the geometry interact. The physics does not depend on the choice of coordinate systems, and what we observe is the high level of validity of the theory in large scales in astronomy and wherever the gravitational field is strong. On the other hand, we have the microscopic theory, we have quantum mechanics and field theory, which however works on fixed background spacetime. Usually in most of the descriptions, maybe outside of some very new formulations, the coordinate systems play crucial role in describing the theory, and as I said, this has experimentally confirmed domain of validity in microscale. What is the problem, however, is that the basic principles which I listed here are mutually excluding. Normally, if the domains of their applications are disjoint, we don't have problem with that. However, we start to observe, and we believed for a long time, that actually in reality there exists domain where both aspects, quantum aspect and relativistic aspect of space-time and matter, do play crucial role, are significant. And this is early universe epochs in cosmology in particular, and black hole interiors. And to describe accurately those epochs, those areas, we need the unification of both theories, which we denote by quantum gravity. Of course, there are various approaches to quantum.
Are there any other areas of physics except of those completely inaccessible by experiments you mentioned, where the quantum mechanics and gravitation theory work?
Okay.
Let me give you an example. We know that general relativity is extremely important in GPS.
Yes.
And also the GPS wouldn't work if not the atomic clocks,
Yes.
which are quantum mechanical devices. And there is absolutely no need to use general relativity to describe the atomic clock, which is a part of the general relativity device, which is called the GPS. So there is completely no problem. We can handle these things with the existing relativity theory and existing quantum mechanics. So
Yes, in case of GPS, indeed.
So is there any conceivable experiment situation except of the creation of the, well, we will never ever get to the black hole, except of the movies.
Yes, yes.
Thor.
Okay, so to answer that question, I have to digress a little bit. So first of all, okay, as far as GPS is concerned, just general relativity to describe motion of the satellite and the quantum mechanics to describe atomic clock are sufficient, of course. As far as dominance of the effects and absolute necessity to have the unified theory is concerned, we believe so far that these are the two domains which are the only ones which really truly need them. Which doesn't mean that in lower energy domains we don't have any effects which would be generated by quantum gravity. In particular, it is believed that some effects of quantum geometry, of quantum nature of geometry on particle propagation should show up in measurement of transition times for very large energy particles like high energy gamma rays. Then we actually expect to be on the verge of observability of...
So what should happen to this gamma ray?
Well, if for quantum geometry effects the dispersion relation describing propagation of the gamma photon is modified, we should be able to observe discrepancies in arrival time of gamma photons emitted, for example, during high energy gamma ray bursts, which are usually billions of parsecs away. And right now we have the ability to measure the discrepancies within seconds. So that gives extremely...
So, theoretically speaking, very high energy Mossbauer effect should show the... I mean, what's the difference between high energy gamma ray emission and low energy? The energy only.
Yes.
Okay, so we know that the Mossbauer effect is a normal energy. Mossbauer effect is affected by the gravity field. That was a Pound and Repka experiment, and it is perfectly described by the classical general relativity and normal quantum mechanics.
Yeah. However,
Dispersion illusion for photons.
Yeah, but that was it. So the question is that if I will do the Mossbauer
In
effect,
other words, in just old-fashioned language, this merger of these two theories would somehow bring the non-linearity to the propagation of photons.
exactly. Yes. Well, in order to
Not quite
probe...
non-linearity, it's still linear but dispersion.
Well, in the sense of...
so it's not like
So
these
this case-
corrections to electrodynamics by Euler and
this-
The
we
difference
would-
with dielectric. The difference
Yeah.
between Mossbauer and this is that Mossbauer is done in a tower which has meters size, and we are talking about parsecs. So this is
yeah, but this is
So smaller effects can be measured.
yeah.
Just propagations. But how do we know when this given measured gamma rays pulse or something, when it hasn't been created? Do we know it to such accuracy?
Well, that's... one has to be slightly careful. We claim that we do. Essentially, the source of the photons are high energy gamma ray bursts, which are quite compact events, both in time and in space. However, of course, we add some theoretical information to that. We add some models, some astrophysical, one can say astrophysical because these are not stellar sources, of course, but one can add some theoretical predictions coming from models of such event. And then everything depends on how well we can actually describe the source.
So we would look at the difference between arrival time of different frequencies. Or what?
Yes,
Yeah.
exactly. And such measurements have already been made, for example. So right now we have not observed any effect of quantum gravity. However, we are able already to give the constraints on quantum energy, quantum gravity effects.
Why do you call it quantum gravity? It's this space propagation in a fixed background.
Right. And also the space, this huge space between the source and the
Yes.
detector is filled with matter.
Yes.
It's dilute, but it's filled with matter. Is it certain that this is not the bigger effect than the...
Well, at the level of energies we are talking about, we essentially have practically flat cross sections of interaction with matter, of interaction of gamma rays with matter. So this we can pretty much exclude.
It's a little bit surprising because certainly these gamma rays interact with nuclei.
Oh yes, definitely.
And then is frequency sensitive.
Yes, but nuclei...
That's the core of the Mossbauer. That the nuclei, that the gamma rays interacting with the nuclei behave differently than the gamma ray emitted. And the very tiny motion of the nuclei in the crystal interact with the very powerful, on a scale of a solid state physics, the gamma rays in atmospheric effects are enormously energetic, right? And we can measure this slight difference. So anyway,
Well,
the conclusion is that there are people thinking that there are possible experiments, and that is sufficient at the moment. Otherwise, we will
okay.
never convince.
All right. So I understand that there are divided opinions regarding whether we will be able to measure it. I would like to somehow try to convince you that if we are not there yet, then we should be there quite quickly. So once we establish the somehow possible need to have the quantum gravity, we of course know that there are several approaches. There is the approach from the direction of particle physics, which is known as the string theory, is the most popular. Another, much less popular, is approach from the direction of general relativity, and it is known as loop quantum gravity. And well, apart from that, there are a couple more, like spin foams, which is the covariant version of quantum gravity, geometrodynamics, much older program, and possibly other approaches. Here, what is important is the requirement of lack of any background space-time, lack of any background dependence. It's a principle taken directly from general relativity. And we do expect that standard four-dimensional space-time will emerge from those theories in semi-classical approximation. And in particular, if we consider the loops and spin foams, we denote them as a kind of discrete approaches. In these theories, we don't even have geometry fields. There are no quantum fields describing geometry. There are more, one can say, exotic, more raw objects like graphs, for example. And then the geometry structure is emergent, is essentially given by expectation values of the observables. So just to focus on loop approaches, we have first, what we need to know are the main principles upon which they are built. So, as I said before, the most important one is an explicit background independence. In particular, we don't initially equip any manifold used to describe the space or space-time with any metric information. We impose explicit diffeomorphism invariance of any theory which we are building. And another, maybe not crucial, but distinguishing the theory is use of non-standard quantum representation, which essentially follows from Yang-Mills theory. Main branches of this loop approach is the canonical loop quantum gravity, which uses the standard 3+1 splitting of space and time and the Hamiltonian formalism. Then there is a covariant approach, analog of path integrals of the graphs, although this is not directly path integral formulation of quantum gravity. This is known as spin foam models. They are following from the theories like Regge calculus. And then we have loop quantum cosmology, which is believed to be a sector of loop quantum gravity used to describe more symmetric models. However, in itself is actually independent theory. It's an application of the methods of loop quantum gravity to symmetry-reduced, usually cosmological models. So, given this introduction, I would like to present a very brief outline of what I'm going to talk about. Of course, I'm going to focus on canonical approach because as far as probing the dynamical sector is concerned, this is much more advanced branch than the covariant one. I'm going to present a brief recall of loop quantum gravity, its basic properties, basic principles, which I already actually listed, basic steps of its construction. Then I'm going, before stepping into the dynamical sector, because it's extremely non-trivial in full theory, I'm going to describe its simplified version, loop quantum cosmology, again its construction, then the dynamical sector, which we were able to probe in many more details than full theory, and then I will switch to dynamical sector of loop quantum gravity, or more precisely what we do know so far about this sector, because as we'll see, we don't know much yet. And in particular, I'm going to talk about the genuine quantum dynamics, about interface between the loop quantum gravity and the loop quantum cosmology, and in something in between those two theories known as the MIDI superspace models. So, what are the main achievements and predictions of loop quantum gravity? First, its main feature is that it's a precise mathematical framework formulated on diffeomorphism invariant level. Second is that the operators corresponding to geometry properties like areas, volume, have discrete spectra. That's why we call this theory discrete. Also, at present, we have certain definitions of, yes?
What's meant by the discrete volume? So we have a space divided into a little coarse grained areas?
No, we have basic objects describing the geometry, which in this case will be graphs equipped with quantum numbers, of which I will present in a moment. And then we can ask about the volume of certain region, which, for example, encloses portion of the state, encloses portion of the graph. And such volume will be given as expectation value of certain operator known as the volume operator. Not really, more like collection of the graphs. The basis of the Hilbert space. Yes, yes, but still it would be collection of the graphs. Yeah, I will present these details in like 5 minutes, I think. So we have good definition of coherent states, so we can build something which resembles classical universe just by coherent states, although this is very unmature construction. We still don't know how it is preserved under the dynamical evolution. One of the more advertised results is reproduction of Bekenstein-Hawking formula for black hole entropy from counting the loop quantum gravity microstates. And in specific frameworks where the gravity is coupled to specific matter systems, we can actually build a complete quantization. We can complete the quantization program and try to control the dynamics. However, as is up to now, we don't have explicit, strict calculations of the behavior of the dynamics of quantum universe. So just to recall basic construction, of course, I will just essentially list the steps. We start with, of course, gravity coupled to matter. As gravitational action, we take the standard Einstein-Hilbert action, then we can couple it to matter, for example, standard model. And for consistency, we need boundary terms. Usually, what we take here to construct quantum gravity, we take the Holst term. Then,
What's this boundary term?
the Holst boundary term. Then, once we have the covariant classical action, we perform the 3+1 splitting using standard formulation with trimetrics, lapse and shift. However, in difference to, for example, geometry dynamics, we don't quantize those objects. We go a little bit further. We introduce triads. We describe metric as product of triads. Then, having these triads, we actually go to slightly more involved object. First, we change the weight of the triad, we perform the densitization, and as second object, we choose the SU2 valued connection, which is essentially given by Levi-Civita and the curvature like this. It's known as Ashtekar or Ashtekar-Barbero connections in the literature presently. And fortunately for us, these objects form the canonical pair with this Poisson bracket.
So extended curvature of this manifold, right?
Yes.
Which is immersed in some.
So far, we're working with classical space-time with 3+1 splitting.
So the idea is that there is a constant time slice which
Yes.
moves through space-time because its geometric existence is known as the Euclidean formalism.
Yeah, well, perhaps it's known under this name to some people, but there are some uneducated individuals who reflect don't know these names.
Okay, so essentially we have the space-time, and then 3+1 splitting is essentially introducing a foliation by constant time surfaces, as Mikołaj have said. And then, of course, on this three-dimensional slice, we have the canonical data. We know that Einstein field equations are the hyperbolic system, and the data we need is the trimetric and the exterior curvature, which one can think about like first derivative of the metric over the time.
It's external curvature of that three-dimensional
Yes.
piece of that immersed in the usual space-time.
Yes. And then we.
It doesn't need to be named.
It doesn't need to
Now,
be.
there were names mentioned.
Okay. Why the names? Okay, names because we are using a specific SU2 valued connection here. So the names come from choice here. Yes. And of course, the well, yes, the one can. Yes. Yes.
I never understood why SU2 is distinguished here. What is the physical reason?
Okay.
This is just a convenient model. Ah, of course, this is
Yes.
just
Technical.
It's simpler. It's the simplest possible.
Partially historical, one can even say, because what happens, like the actual property, the mathematical property which is relevant is the symmetry transformations of the triad, which are the rotations. And then second
It's a pure game because it is just a choice.
Of this trial.
Information about metric is much less than the choice of trial. But okay, you may encode it in a choice of a trial, but then you have a huge gauge group.
Yes. So
in a way, it's just a parametrization.
yes. And then why SU2? Because essentially, due to duality between SO3 and SU2, we can shift to SU2, and we do it essentially because historically the methods developed for quantum gravity come from Young-Mills theory. So then it's obvious formalism coming from Young-Mills, which we want to somehow at least initially mimic here. So that's my understanding of why actually SU2 appears here. Of course, given that we perform the canonical transformation, we perform the Legendre transformation, bring the action to its canonical form, and then, as always in general relativity, we produce algebra of constraints. And in particular, we observe that we don't have the physical Hamiltonian. Instead, we end up with Hamiltonian constraint, which is one of the elements of this algebra.
What is unusual in this trick, because things are, some of these assumptions are just classical, but what is unusual is that in the standard canonical gravity, three-dimensional metric, which is here represented by this is dual to K, to extrinsic curvature. But K is not a connection, and therefore, in order to be able to use those techniques taken from lattice gauge theory, we add gamma, which is connection. Gamma is really connection. Then if you take connection, you add something, a tensor, you have again a connection. So this is this unusual trick, and it still remains canonically conjugate to Q, because gamma is essentially Q. So if K is momentum, then A is something like momentum plus position. So momentum plus position is again momentum. So roughly speaking, this is the origin of this trick.
Okay, so what are the elements of this algebra of constraints? Since we are using triad formalism, we have a little bit more than just diffeomorphism and Hamiltonian constraints, which in
I don't
chosen.
understand how you can add the momentum to position.
Of course, you could shift.
Oh, of course. If
that way.
commutation relation between position and momentum
the
is
dimension.
standard, then commutation
There is
relation
there
between
must be a
x and p
parameter
plus something like
which
x
is very
exactly
strange
the same.
dimension.
Not very strange. Very
It's,
No.
it's mass over time.
Yeah. So, well,
Yeah, of course. You have to choose parameters, and these parameters are appropriate.
So what is the
Well, here we.
mass time? What is the
no.
The
that was
momentum
just-
plus some constant times
from where you get the value of it?
But here it
it is a choice.
We anyway have the
Yeah.
gamma, which can incorporate
It
the
is
freedom of choice. Yes. Well, and this gamma is not determined by any principles here. It's essentially something which, as long as theory is formulated, it's given
It's a
freely.
constant in the theory.
Yes, it's a new constant in the theory, and essentially later we will see that it corresponds to somehow coarse graining of the graph used to describe the geometry. Not a coarse graining, but like how fine the graph is. Now,
appear in this theory at some point?
yes.
Connected to this gamma?
No, not particularly to gamma. Gamma is dimensionless parameter, but it will appear nonetheless soon, yes. So we remember that so far all these objects are classical, so there is no edge bar by definition. So just to focus again on the loop quantum gravity algebra of constraints, we have three generators, three constraints. One is known as the Gauss constraint, which is analog of the Gauss law, and it essentially describes the freedom, gauge freedom of the triad elements. Then we have the somehow modified by the Gauss constraint, the diffeomorphism constraint of general relativity, and at the end the quadratic Hamiltonian constraint. And they, unfortunately, in the variables which we have chosen, they are described in this a little bit complicated way. FAB is a field strength, or essentially it's a curvature corresponding to this connection. It's a curvature of this connection. Since this constraint algebra, it's a Dirac algebra, although not with the structure constants but structure functions, we can try to apply the Dirac quantization program, which consists of 3 steps, which is quantize system ignoring the constraints, express constraints as quantum operators, and then extract the physical sector of the theory as a kernel of quantum constraints operators. So right now, so far, it's just general relativity in some strange variables. So right now, we are actually entering the characteristic elements of loop quantum gravity, and one of them is that instead of metric and the exterior curvature, as our basic candidates for quantization, we will use the something which we can call analog of Weyl algebra in quantum mechanics. Instead of the connections, for example, we will use the parallel transports of the connections along some curves. Gamma here denotes the curve. It has nothing to do with the parameter on the previous page. These are our holonomies. And then we also integrate our densitized triads over surfaces, forming fluxes of the triads. And all these objects form the so-called holonomy flux algebra with the Poisson bracket, which is strictly inherited directly from this Poisson bracket. So, given that, we can build the kinematical stage of loop quantum gravity, and this is performed by the so-called Gelfand-Neumann-Segal construction. And of course, this has been developed over a long time. Right now, it's practically almost 30 years of development of this component of the theory. I just list here the results because it's a complicated process. We end up with Hilbert space, which we call the kinematical one, and this space is spanned by the so-called spin network states. These are its basis elements. And what are these spin networks? Essentially, these are the graphs which are embedded in 3-dimensional oriented manifold. However, there is no metric information on this manifold. It's just the topology which is needed. These graphs have edges and vertices, and edges are equipped with half integer with spin labels, which essentially label the representations of SU2. And we have intertwiners on vertices. We can think about them a little bit like analogs of Clebsch-Gordon coefficients. Essentially, what happens here is for practical purposes, one can think about the intertwiners as equipping each vertex with virtual subgraph. So one can think about each vertex as some graph which will have 0 size, of which distribution is not a graph which is not distributed on the manifold which we use for the description. It's the internal object, and the only important data there is again distribution of spin labels inside it. So if we want to describe the intertwiners, we have normally, one can say, the physical graph, the actual basis function, and then we equip each vertex with the subgraph structure. So, yes?
Can I draw arbitrary graphs in the two-dimensional space and they will be basic of a theory?
Yes. There are certain restrictions. Yes. Yes, indeed.
It is theory of all possible graphs.
Yes.
And that contraption is used for every possible, I mean, you did it for a graph where 4 lines join.
Yes.
But if I have all possible graphs, I may have a graph where 7 lines.
Yes. And then we use it
How
for.
do I do it?
Well, it's the same question as adding angular momenta in quantum mechanics. So there are various ways of adding them, and the transformation between them is provided by Clebsch-Gordon coefficients. And we have analogous transformation here. So we can always, even if we have, say, 7, 8, 95 edges entering one vertex, we can build the structure of essentially.
So there is a prescribed procedure how to split, and what is the lowest vertex 2?
Lowest non-trivial is 3.
3.
What?
Yes, however, what enters the theory is that if we have 2, essentially, because of the Gauss constraints, they have to correspond to the same label, and then the internal structure of this vertex is trivial. So essentially, we have trivial reduction, which just brings it to a single edge. So the lowest non-trivial vertex is trivalent.
They are purely mathematical contractions. There's no physical intuition behind in drawing all these graphs.
There is.
Angular momentum, right?
Yes, it's an angular momentum, and essentially it's
So what
as
the
you.
word is built up of the graphs carrying the angular momentum.
Well, it's representations of SU2.
Graphs are
The numbers, the quantum labels on the edges,
well, you'll
but
associate these quantum labels to the lines or the vertices
Yes.
according to some additional rule. I'm asking about what is the physical intuition behind the fact that the universe should, can I finish, consist of these graphs to which you choose arbitrarily, as we discussed before, the SU2 labeling. Why SU2 labeling and not the other?
okay, so we go essentially up to the previous question,
Yeah.
because our origin is which we've chosen for whatever reason, convenience, historical, we've
Now
chosen
that's
SU2
what
connection.
I'm asking.
Yes,
What
yes.
are those reasons? The rest is a beautiful mathematics.
Because it works. This representation works.
It works, and it's,
But we don't know, maybe there is another
Of
one.
course, there are absolutely.
and that
So
would
that's
give
what- so
in
why
equivalent
do we
theory.
Pick up that one. What is
Because
the
Ashtekar decided that that's a nice trick to parameterize the degrees of freedom. There's absolutely no deep reason except
Yeah, okay.
mathematics.
But this was the answer I wanted, not from the, I'm sorry.
Yes, yes, but I'm sorry, I was under impression that I already told it here, that it's a matter of convenience and more like history, where we essentially, not we, but the people who originally developed it
You see,
wanted.
the words have a certain meaning in physics.
Yes.
And maybe I'm old-fashioned physics. I mean, the convenience in solving physical problems means that we do some approximation, but anyway, there is a physical reason why that
No, quite often it's just a choice of a reference frame, for instance.
No, but this, may I just say to quantize quantum a system with infinitely many degrees of freedom is a hard job. And
this I
often-
agree.
Yeah. So the way in which has been chosen here is to somehow distinguish a finite number of degrees of freedom. And for instance, there are many ways to do it. For instance, some smearing, to calculate some average value of the fit. Here you choose a graph. And with this graph, you assign the following things. First of all is this connection. Okay, connection when integrated, it integrates to a Wilson loop, in quotation mark. Yeah, Wilson loop is an element of a group. Which group? Rotation. SU3. Then you replace it by SU2, just because it is much more convenient. So you know already what is this SU2 element related to every closed loop. It is, roughly speaking, the integral of A of this connection along the loop. So this is one degree of freedom which is assigned to every loop. And another is this A, which is another story, but roughly speaking, it is again some integral, it has been written somewhere, integral of the integral of the metric. But this time it is integrated over the perpendicular two-dimensional surfaces. So you replace infinite degrees of freedom by finite number of those integrals. And that's all.
Not really finite, because you can choose any surface.
Yeah, but for a given graph, of course, and then you would like to consider all those degrees of freedom, which means all possible graphs.
But at a given instant, we're working with one graph, which reduces the complex geometry of this thing to one single graph, which we can conference, let's say.
But for each graph, you have quantum mechanics of a finite number of degrees of freedom.
Well, countable, because the graphs can be still infinite. However, we have to remember that single graph is just support of a basis element. It's not like universe is a single graph. The state describing universe is supported on all the collections of the graph. Okay, shall I continue?
Yes, sure.
Okay, so one problem with this construction is, of course, that because we have such large number of the graphs, we have continuum of the graphs, our Hilbert space is non-separable. And this is one of the, how to say, more difficult problems of the theory, because we have much more difficulties in working with non-separable spaces than with separable ones. Most of the theorems which we use in quantum mechanics, quantum field theory, are actually restricted to separable Hilbert spaces. And even if we try to build semi-classical states to introduce any kind of statistical canonical ensembles, we actually are not able to do it anymore. So, important part.
However, in physics it doesn't really matter. Even in ordinary quantum electrodynamics, we have non-separable Hilbert space when we include the infrared problem.
Oh, yes.
One doesn't care whether it's separable or non-separable.
Some people
Because
don't even know what
that would be important if you wanted to prove hard mathematical theorems. However, if you deal at the level of physical intuition, then the difference between separable and non-separable
problem here is that we are actually trying to develop theory which is well outside of what we so far were able to observe, which is essentially a theoretical extension of certain theories which we know describe the reality accurately. So in this case, we don't have much of physical intuition. So the mathematical rigor becomes somehow the leading force in developing those theories.
But are you really hoping to prove hard mathematical theorems in this context?
Everything depends on what we consider by.
You can do it in ordinary scalar theory if there is an interaction. It is already a hopeless task. So here I think it's.
Well, that will strongly depend on the theorem we want to prove, so I cannot really say much. Anyway, the idea of development was to go with as much rigor as we possibly can. So we want to be able to construct canonical ensembles in the theory, and for that we need, for example, separable Hilbert space. So that's. Well, it is a problem if we want to use the standard techniques to extract the dynamics also. So I would guess that I would say that this non-separability problem will show up even on the sector of loop quantum cosmology, which I hope we'll be able to see in a moment.
So in other words, there is this very deep and intriguing and important mathematical subgroup will have for example, a repercussion on this gamma ray experiments you mentioned?
Can. Definitely it changes.
Everything can happen.
Oh yeah. What I can say for sure is that in certain models of loop quantum cosmology, this feature affects the dynamical prediction.
And those predictions are in agreement, disagreement with whatever the theory predicts experimentally, or they are just
Well, so far they are.
which have not relation to.
They are
so far,
conclusions.
let's say.
They are conclusions which had no, so far, observational confirmation or falsification, yes.
So if this Hilbert space is separable, the results will be that, and if it's non-separable, the results will be this, but we have no way to tell which are
No,
better.
not even that.
In fact, separability versus non-separability is not the starting point, because the starting point is how you relate different graphs. If you have a big graph which you divide into two parts, the crucial problem is how to relate quantum description of those physical subsystems with this big physical system. And the way which is used here leads to a non-separable
Those
graph.
graphs should not be
So why you say
similar
the
in some sense.
separability is just a result of a certain treatment of the
QED in the finite volume is actually supporting separable Hilbert space.
Yes.
Now, presumably universe is also finite, closed, yes. Does it have any influence over the separability issue?
No. Because even if universe is compact, we can consider spherical or tritorus spatial slice, and we still have the continuum of number of these graphs, so no.
Because if you choose finer and finer splitting, say, you get non-separable space even for a finite one.
In other words, there is no analogy to the infinite.
Yeah, it is a different way to handle subsystems of a system. This is the main difference between this and the standard way which we encounter, for instance, in electrodynamics.
Non-separability enters in the ultraviolet, not in the ultraviolet. Finite volume kills, yes.
And
Yeah,
unfortunately,
because this non-separability which you mentioned is in a sense trivial, because it is somehow labeled by boundary value of the field
Yes.
at infinity. Once you fix it, everything else is separable. Here, the origin of non-separability is completely clear.
Comes from small distance.
Yeah.
Yes. So unfortunately, I won't be presenting this model, but one can consider the idea even of, say, isotropic space-time.
Well, I still have a problem here, because it would seem that when you start quantizing, you should encounter the Planck length, which will somehow limit the graininess of the universe.
This graininess will be emerging here in a different manner, unfortunately.
No scale built on the
But Planck length must enter here. You cannot
Yes.
go deeper
So
than
where?
and there's only after quantization, not
Yes.
before.
Yes.
But
So
Hilbert space is also quantization.
yes. So what happens?
But there is no time scale.
In other words, things are set
involved
on what they
those
see.
abstract graphs, because you.
No, I understand, of course. But after quantization, you have H bar and then
Okay. So where the Planck length actually enters. So we have basis of our Hilbert space, but then of course Hilbert space is not enough. We need observables, and we can consider the simplest observables volumes and areas. And in particular, we can construct the operator. Unfortunately, I don't know if I described it, probably not. The operator corresponding to the area of surface intersecting the graph in some manner. For example, we have maybe more complicated graph here, and we consider some surface. And then we may ask about the area of this surface. It will be given as expectation value of certain operator, and the operator has a discrete spectrum, which moreover is built out of isolated systems.
But it must contain Planck.
Yes. And then, of course, we have spectrum, we have 0, then we have certain positive values, and the,
But the surface then is in unit of Planck length.
yes, of Planck area.
Right.
Yes, indeed.
Yeah, well, that's the same.
But if you take an abstract graph, you cannot decide whether it is small and of the Planck length, or it is huge.
No, no, but I'm talking about the
the
surface.
difference is only
No, but
in his
the surface.
in his quantum state.
Yeah, but the other element, the surface element, of course,
This is an abstract surface.
what do you mean abstract? Does it have dimension of L squared or not?
Only when you know its quantum state. Classically, there is no.
No, no, that I understand, because there is no unit that you can use. Not use the length.
So
The
just
same abstract graph may describe you something which is extremely small.
and extremely large.
When it is in a different quantum state, it may describe something which is extremely
But when
great.
it's quantized, then it means that the quanta are in unit
Yeah.
of surface.
Yes. Yes. So just to repeat, the manifold in which
And
the
if-
graph.
And in the spectrum, there is a gap, I understand. There is the
Yes.
smallest possible.
Yeah.
Yes, so there is essentially gamma LP square term.
This is the problem with non-separability, because you cannot go.
No, it doesn't. This appears in spectrum of the operator. This is a property of the spectrum of the operator. Not. It won't help with non-separability, because if I right now want to construct the state of the universe, I will have to take again all these possible graphs. And that's where non-separability enters. So the fact that the spectrum is discrete of the operator acting on particular graph, that doesn't help. However, what happens is that we observe certain subspaces, essentially some structures or topologies of graphs, which are preserved under action of our operators, which we use to even form the dynamical evolution. And then each invariant subspaces in itself is separable, and then introducing natural Lebesgue measures, essentially we can again, it's an artificial construction, but we sort of can construct separable Hilbert space, treating each Hilbert space corresponding to a sector as a fiber of the final Hilbert space. The same problem appears, for example, when we, in quantum mechanics, when we deal with periodic potentials, where essentially we reduce the problem. Again, Hilbert space is built as integral over fibers, and each fiber corresponds to compact system with specific boundary conditions. So similar trick one can apply directly in loop quantum cosmology models. In loop quantum gravity, it's much more complicated, but nonetheless, it's at least up to certain fine details is possible. So we can introduce nice separable Hilbert space. I have to say something about the Gauss constraint. So fortunately for us, the action of the Gauss constraint just selects very nice subspace of all these possible kinematical states. So we can just work with those subspace, with this subspace, and we don't have to worry about any.
I have to warn you.
Yes.
Of course, it's partly our fault that we disrupted your exposition, but the time is running.
Okay. So then the question is actually what the audience would like to hear, because I will not be able to present much. I can just essentially gloss over the remaining steps. We can immediately solve the Gauss constraints. Essentially, our selected solutions to Gauss constraints will be, again, those spin labels with spin networks with spin labels restricted by analogs of angular momentum addition rules. Then we use a quite, one can say, exotic method for solving the Diffeo constraint, where we don't have the generator of infinitesimal diffeomorphism. We just use the group of finite diffeomorphism and perform the so-called group averaging. And then it's very nice observation that what diffeomorphism does, it just moves the graph on the manifold without changing it. So for as long as our observables just see the topology of the graph and the quantum labels, they will be invariant under the diffeomorphisms. Of course, then there is the Hamiltonian constraint, and here the treatment is to treat it as a generator. We essentially try to represent in quantum theory the generator, infinitesimal generator. And normally the Hamiltonian part of the Hamiltonian constraint is expressed in terms of triads, curvature, exterior curvature, which are not our objects for quantization. So we have to express them in terms of triads and in terms of holonomies and fluxes, and that leads to a so-called Tiemann regularization. And at the end, the result is the quite complicated combinatorial operator mixing the quantum labels, of which action essentially mixes various closed loops on these graphs. And unfortunately, it's sufficiently complicated that I would not be even able to fit the form of its action in here, so I don't present it. The problem is that now we have to find a kernel of extremely complicated operator, and so far nobody managed to achieve that. So we had to find different solution to the problem. And the solution comes essentially from loop quantum cosmology, which is the simplification of the theory. We use the same mathematical framework and apply it to cosmological systems. For example, in that case, if we consider isotropic Friedman-Robertson-Walker universe, we have the preferred gauge because we have foliation by homogeneity surfaces. Then we have choice of the gauge in which the connections and triad can be represented by certain, again, distinguished triads and cotriads and single pair of coefficients. Holonomies take a very simple form. Essentially, to separate out the connection and triad, we only need to consider the holonomy along the straight edges and the fluxes along unit squares. And the unit squares and directions of these edges is essentially decided by chosen fiducial triad. By fiducial, I mean essentially triad which is constant in comoving coordinates.
What does it mean unit here? Unit with respect to parameters, yeah?
Yes, yes.
Length.
Indeed, there is no fixed length, and there is a bit of care taken in order to formulate the theory in a way that it's invariant with respect to all possible choices of this. So what happens here, I will maybe, what happens in quantum cosmology is, for as long as we consider homogeneous universe, the Gauss and differential constraints are satisfied. The only thing which we have to deal with is the Hamiltonian constraint. The kinematical Hilbert space, analog of the one in LQG, is square integrable functions on Borg compactification of the real line. Sorry?
This is not news.
No, it's his brother. And again, we have operators corresponding to holonomies and fluxes. One of them is the unit flux operator, and holonomy can be decomposed into these operator components. This will be our basic operators. We can label basis of our Hilbert space by eigenvalues of this operator. Then proceeding with the original form of the Hamiltonian constraint, we can regularize it, express it in terms of these operators, and at the end we end up with the operator which has the form of the quadratic or second order difference operator. And this form of the operator is known, so we can actually calculate things. We can try to trace the behavior of the state. And okay, originally people following the geometry dynamics tried to define the evolution of the universe as evolution along the volumes. One has to say that this operator is related in a very simple way with the volume of at least certain portion of the universe. And well, this is an early attempt from 2005 of numerical simulation, where one defined the Gaussian semi-classical state as defined on fixed volume and tried to evolve it towards a singularity. However, what one observed was this kind of amplification and split, and this is very known picture in quantum mechanics. It's just inverted, rotated by 90 degrees picture of particle tunneling. So that gave the new paradigm, where essentially we decided that we need to use the matter fields as time and abandon using the volume as time. Then our Hamiltonian constraint takes the form of simple Klein-Gordon equation, and then we can use all the quantum mechanics of Klein-Gordon system to probe the dynamics. And well, this is example of semi-classical state. What is important is that we still deal with the constraint, so there is no per se time evolution. We can solve the Hamiltonian because we can track the spectrum of its component operators, and essentially the solution is analog of the Klein-Gordon. The Hamiltonian constraint has a form of Klein-Gordon equation where phi takes the role of time and v takes the role of the space coordinate. And again, the elements of Hilbert space are wave packets with certain spectral profile. Although problem is unfortunately that these basis elements, equivalent of plane waves, have quite complicated form and have to be defined numerically. As observables, we use.
Slowly finish.
Okay. So, as observables, we essentially choose the formalism of partial observables, where we choose single slice of the matter clock, and then act with kinematical observable and complete the result to the physical state using this formulation. And that gives well-controlled dynamics. In particular, it gives this advertised big bounce, where the contracting semi-classical branch in high energy regime transforms into expanding universe. Of course, there is a lot of confirmations and extensions, presentations to which unfortunately I don't have a time. So this is the description of numerical tools which we were using. So far, the most advanced ones is the numerical library, of which I'm the main developer. Modification to the Einstein field equations, which can be derived in quite general form. And, well, in terms of loop quantum, when it comes to loop quantum gravity, what we essentially have to do is to use the same idea, to use matter fields as clock. That leads to very known procedure known as deparametrization. In particular, the deparametrization with respect to dust was introduced in the 90s by Brown and Kuchasz, later modified a little bit by Kuchasz and Torre. And this deparametrization is used in loop quantum gravity, at least in one of the forms of loop quantum gravity. When we split the Hamiltonian constraint and choose appropriate gauge associated with the or agreeing with choice of matter field or certain potential of matter field as time, we can reformulate the quantum constraints as an analog of the Schrödinger or Klein-Gordon equation. Here, in case of use of the dust, for example, we have analog of Schrödinger equation. And then, for as long as we know action of this operator, we can already evolve it. And that was the idea. So at present, what we are able to do, we are starting numerical evolutions of loop quantum states. We are considering so far very unphysical models of very simple graphs and try to control essentially try to solve numerically this Schrödinger equation. One partial result is, for example, presented here, where we have one main component of Hamiltonian constraint, and this is support of its matrix element on states corresponding to a very simple node, very simple spin network, which is essentially for valent node. And of course, we have more approaches, the consistent relation between loop quantum gravity and cosmology. We have quite firm control over interface between theories right now, a little bit less in full theory, but for as long as we consider simplification, for example, we replace SU2 with U1 cube. There are works within like recent works like past year, which provide quite nice control over the relation between loop quantum gravity of coherent states representing universe and loop quantum cosmology representation of such universe. And, well, maybe I should finish here.
There's one thing
Yes.
of gravitational field. And instead of using it in a controlled way so that you can find corrections to observable effects like the lamp shift, you go into the domain where there's no control whatsoever. There are no experimental ways of testing this. Has anybody tried to apply this to a very simple problem? What are the corrections to the lamp shift which come from this quantization procedure?
Well, people try to. Are you asking of application
But
to loop
they must be
quantization?
small, so it's easy to calculate them because they're perturbative.
Well,
It's very dangerous when you have a problem which you think you solved in all generality, like quantization in terms of these loops. At the beginning you said we can quantize the gravitational field. Okay. Now the question is, can you find some predictions that can be tested experimentally?
well, yes,
Or
that's.
even what are the orders of magnitude of these corrections?
Okay, so what happens? At the level of loop quantum cosmology, at least, we have very firm control, and essentially these bounces occur at order of Planck energy density. So this is a firm physical prediction. As to
But
confirm,
this is within this simplified cosmological model.
Yes.
I'm talking about laboratory systems.
well, yes,
Where you
then.
cannot use your simplified model.
Oh yes, indeed. And then we have to go to full theory, try, and that's the program of controlling the dynamics, which is still in early